Alright, this video is going to take a look at a work energy method to develop the elemental stiffness matrix. And this is important because it's necessary to start deriving the stiffness matrices for the 2D and 3D elements. And so sort of have these drawings of our old energy type drawing here, potential energy type drawing, and how we're going to use that to figure out our stiffness matrix equation. In this case, for a truss element, we're going to use that as an example. Okay, so why does this matter? And the mechanics methods that we used for our truss and beam elements, our frame elements, our springs, well, it really only works for those. Moving on, we have to use the energy approach. And so we're going to use that for our 2D and 3D elements. There's actually another approach that we could possibly use, but for now we're just going to use the energy approach. And so the main assumption that is used in this is linearity. And so if we have this drawing of a spring, and if we pull on that spring, we assume that the amount it deforms will increase linearly according to how much force we pull on it. So linearity, that's the big assumption underlying the energy approach that we're going to be using. All right, so we're going to go ahead and introduce Castigliano's theorem. So you could also use principle of minimum potential energy. That also works to give the equation that we need to work with, but we're going to use Castigliano's theorem. And the reason is because, well, it's pretty straightforward. Let's go ahead and say that this is the strain energy that we have under the curve, right? So force displacement curve, like you were pulling on a spring, linear, because that's the main assumption we need to use. So we're just going to say the area under the curve is our strain energy, and also written as potential energy, if you might remember back in dynamics. All right, so now we're going to go ahead and say, like, what if we pull on it just a little bit more so that there's just an infinitesimal amount more displacement. So we're going to go ahead and look at that. We're going to say, like, well, this is some infinitesimal change in the strain energy. And we could say that infinitesimal change in the strain energy is roughly equal to that force P, right? I mean, if it's an infinitesimal change in strain energy, that magnitude is not going to change very much. So it's that height P multiplied by that width, which is dq, or the infinitesimal displacement. And so, using that, we just go ahead and rearrange things. Okay, it took me a long time to draw that, probably too much than was necessary. It gives us our first Castigliano's rule, which is the force P is equal to the derivative of our total strain energy in the system with respect to given displacement. We're going to find later that displacement corresponds to the same location and in the same direction as that force P, or that load P, because it can also apply to moments in addition to forces. So here are some notes. The first note is that it works for any linear system. And so just like we drew it for a spring earlier, here's a cantilever beam. As long as we can assume linearity, Castigliano's theorem will work. And it also works for multiple loads. So that means if we have one load and a corresponding displacement there, we can have add another load, and both of these equations would be true. And just like we have it for forces and displacements, we can also have it for moments and rotations. So if we had all three of these loads, we could have all three of these equations. Note that in each one, the displacement corresponds to the same location in the same direction as the force, or the rotation corresponds to the same location in the same direction as the moment, which is exactly what our fourth bullet point is. Okay, so that's really all the theory. Now we're just going to go ahead and take a look at how we would use Castigliano's theorem to derive a stiffness matrix for a truss element, because it is something that we are already familiar with. All right, so the first thing we do is we want to find the total strain energy in terms of our nodal displacements. So let's go ahead and say that we have a part of a truss here, right here, like some infinitesimal portion of that truss, dx. And through that infinitesimal portion, we have a force f of x going through it. And so because of that, we have an infinitesimal displacement, du. All right, so now we're going to go ahead and draw this diagram here where the force being pulled on it and our infinitesimal displacement there. And we'll say that that infinitesimal displacement gives us our infinitesimal change in straight energy. All right, so we have this equation here. All right, infinitesimal amount of straight energy equals 1/2 times the force times the infinitesimal displacement. So we're going to go ahead now, keep moving through this, we're going to go ahead and substitute that infinitesimal displacement using Hooke's law. Remember, we got to get this in terms of our nodal displacements in order to do anything with it, in order to apply Castigliano's theorem. So we're using Hooke's law, go ahead and rearranging our expressions for our stress and our strain, and rearranging this to find an expression for our infinitesimal displacement and plugging it back in over there. And if we plug that back in over there, we get the following equation. And if we integrate that equation, we can find our expression for the strain energy within a truss bar. All right, so now we're drawing our truss bar with forces at either end and displacements at either end because we need to get this in terms of those displacements. So we're going to go ahead and redraw that and make an expression for f of x. Once again, we got to get this in terms of these displacements in order to use Castigliano's theorem. All right, so in order to do that, we go back to Hooke's law. And so we have this equation that we had earlier, all came straight from stress is equal to elastic modulus times strain for one-dimensional Hooke's law. And we go ahead and take our displacement function, which can be written in terms of our shape functions and our nodal displacements. And so we have this written here. Remember that this shape function for node 1 is equal to 1 at node 1, and it decreases linearly until it's 0 at node 2. Similarly, node 2, that shape function is 0 at node 1, and it increases linearly until it is 1 at node 2. All right, so we can go ahead and write our displacement function u of x in terms of individual shape functions for those nodes and their corresponding displacements. And so if we take the derivative of that, then we get an expression as follows. We get an expression in front of our displacement at node 1 and in front of node 2. Still solving. Okay. So here we go ahead and make that substitution for our expression f of x, and we can plug that into the equation for our strain energy. And if we do that, we get the following, and hooray, now we have our strain energy in terms of our nodal displacements. And we go ahead and take out the integral because we're going to go ahead and assume that everything inside here is a constant. All right. Hooray, we got that part. That's the largest part. Now applying Castigliano's to find the truss stiffness matrix is done as follows. So there's our expression for our strain energy in terms of the nodal displacements. We apply it once at node 1. Remember that we can apply Castigliano's to any, we can apply it to any location that has a force applied to it and has a displacement at that corresponding location in the same direction. And so that's exactly what we're doing here with our truss element. We have node 1, and we're going to do the same thing to node 2. And once we have those equations, then we just combine them to form the stiffness matrix for the truss element. All right, so these are the equations that we had from the previous slide. And if we just go ahead and rearrange this to put our force vector there on the left side, our displacement vector on the right side, we can go ahead and then come up with our stiffness matrix for the truss element. And hooray, it's the same as what we had before. That's always good, because if it wasn't, then, well, then I'd have to stop the video because I have to go all over and start all over again. Great, so with that, we have some reflection questions. the first reflection question we have is, when we look at Castigliano's theorem, what are P and Q, and how are they related to each other? The next question is, what is that capital U, and what does it need to be in terms of in order to apply Castigliano's theorem? Next, what big assumption does Castigliano's theorem need in order to operate effectively or correctly? And lastly, how many times would Castigliano's need to be applied to derive the stiffness matrix for a frame element? Let's assume that's a frame element in 2 dimensions, which has axial stiffness, and it also has transverse and bending stiffness. All right, and that should conclude the video on Castigliano's theorem, or the work energy method for deriving stiffness matrices in finite elements.